a longer bio. Okay, so first of all, thank you for everybody who's here. I know it's spring break. So that's wonderful that you're here. And I'm also very happy to introduce Professor Shmuel Klein. And he and I have a lot in common. We were both department chairs. He survived much longer as department chair than I did in the computer science department of Bar-Ilan University. And his research is in data compression. And he has published 2 books with algorithms, which are used for teaching. Right? More than 100 scientific papers and several patents, and he retired recently, and since then he has started working in a startup. He just told me over lunch. So welcome, Professor, and we give you 35 minutes to talk because that's the attention span of of students nowadays, and then I will ask you a couple of questions. We will sit over there. Okay. So,
thank you, Professor Geller. Thank you, first of all of you, for coming in the middle of your spring break, and it's really nice of you. Let me try to see if this works. I hope to squeeze my talk into. I was told that it can be whatever I want, but not more than 35 minutes. This is the first rule, and I'll stick to it because I'm working in data compression. So whatever information I have to convey, that's my job, to try to compress it into whatever time it is. So specifically, I'm not able to spend the whole area of my expertise or of your expertise. So I've chosen a specific topic so that you can go home and have something with you. And so what I've chosen the topic of the usefulness of Fibonacci codes, and if you don't know what the Fibonacci code is, that's fine, because I'll define it and give you all the information. So this is my name. I'm worked at the Bar-Ilan University, and so thank you again for inviting me. So let me first put the topic into context. I'm aware that I'm in the data science department, so what does it has to do with whatever you're doing here? So if you take the whole area of data science, it has, of course, many aspects, and one of the aspects of data science, which is a subtopic, has to do with storage. Data science became interesting only when the data grew to be so large that you have to have entire university departments to deal with what to do with the whole data. And part of the data we want to store, but it's not only to store. Sometimes storage, I include into it also the transmission of data, even if they are not physically stored somewhere. But I have a lot of data, and everybody using a mobile phone or whatever, and computers, they have to communicate. You have to transfer lots of data from one point to the other, and this takes up bandwidth, and you have to deal with it. This is one of the problems. So within the area of storage, we are concentrating on a sub-area, which is compression. So you see that I tried to compress the word compression a little bit. Why should we compress? Because data contains a lot of redundancy and repetitions, and it makes no sense to transfer the same data more again and again. And there are, of course, much more sophisticated methods to squeeze out of the data things that really don't need to be there in order to understand it. So what we are actually doing, and all of you know algorithms like zip, and we use them every day. So we get some data, we squeeze it down. So instead of having 5 megabytes, we can squeeze it to 2 megabytes, and that's the way we store it. If we look at it, it doesn't look really understandable, but the computer knows how to invert this procedure and get back. So all these algorithms are reversible, and you get back the information you have. But actually, you have stored or transmitted over some wire only half of the amount you needed, and this is the main purpose. Sometimes we don't so much care about keeping the entire information. For example, if it's a picture, if it's video, in a picture, you know, we can encode today millions of different colors, but our eyes are not able to detect them all. And the same thing for audio. You have an audio file with many of the pitches a human ear cannot hear. Dogs have a larger range for what they can hear. But if we can throw away much of the data so that at least visually it looks for us as if it is the same, and this is then it's fine with us. This is called lossy compression, and we do it every day with our JPEGs and pictures. You take a picture with even with your phone. It has every picture 30, 40 megabytes of data, and you squeeze it down to 1 megabyte, and really only if you blew it up, and then you see that it's not really the same, but it's fine and good enough, and otherwise we would run out of data even faster than we do anyway. So this is what compression is all about. And even in compression, I won't give you the entire background on compression. I'll concentrate on a specific coding called Fibonacci code. And here it is. It's based on the Fibonacci numbers, and here's the background. Everybody of you are surely familiar with the Fibonacci sequence. The Fibonacci numbers are defined in mathematics as starting as a sequence that starts with 0 and 1, and then every number is the sum of the 2 previous ones. We all learned this in first year. And here, this is a picture of the electric plant in the city of Turku in Finland. They have these numbers on the chimney, and without any explanations. And this can be seen all over the city, and you have 200,000 people running away. What is this number? What are these numbers? And so everybody who learned a little bit of mathematics recognizes the sequence of Fibonacci numbers. So they are very famous. They started a few hundred years ago. And you know that you can represent every number as powers of the golden ratio. The golden ratio is 1.618, and its complement. And these are like many of these sequences. You can represent them. These are irrational numbers, and it's very interesting that you take irrational numbers, you raise them to integer powers 1, 2, 3, and by some magic, you divide by square root of 5, which is also an irrational number, and you get integers. You get actually the entire sequence, but this is not new. And you know the golden ratio. If you don't know, just look it up. And Wikipedia golden ratio is known since the antiquity, and It appears almost everywhere in the pyramids. Here you have the Acropolis, and it's used in architecture, in paintings, and many other things. The golden ratio is very popular since the days of the Greeks already, and the Fibonacci numbers are just based on them. And so here, this is the sequence: 1, 2, 3, 5, 8, 13, and so on. This is the famous Fibonacci sequence, and I want to show you a few applications of this sequence and of the properties of these numbers. So first of all, let us talk about basis elements of a numeration system. What is a numeration system? You know that there are binary representations of numbers. Everybody studying a little bit about computers knows that our computers insist on talking to us in binary, so we don't write the numbers as if the way we write them, but on a binary basis. So we take the standard system takes just the powers of 2, 1, 2, 4, 8, and so on. We write them from right to left, and these are the basis elements. And if we want to represent, for example, the number 45, so we represent 45 as a sum of powers of 2. So 45 is 32 and 8 and 4 and 1. So we put the 1 there, and we put zeros for the rest. And this, what you have written here, these zeros and ones, is the binary representation of the number 45. This is standard, but it's not the only one. You can, for example, use other basis elements. For instance, let's try to see what we get if we're using the Fibonacci numbers as basis systems. So we can do the same thing. So we take the number 45, and every number can be represented as even in a unique way, if you start always from the larger one, as a sum of Fibonacci numbers. So 45 is 34 and 8 and 3. And you put the ones there, and you can add the zeros in, and you have another binary representation. So why should we do that? What's wrong about what we did before? Especially that these numbers, the Fibonacci numbers, they grow like 1.6 to the power n, while these are powers of 2. That's 2 to the n. So you need less basis elements in the standard binary than in the Fibonacci. So actually you can measure that. It's 44% more for the Fibonacci number. So why should we do that? Because there is a special property. Now, the property is that there are never adjacent ones in the Fibonacci representation. And that's very easy to see, because how do we represent the number 45, or for instance, any other number? We try to fit in the largest Fibonacci number. Say in our case it is 34. But then I say the next Fibonacci number is surely not in there. Because if it were also 21, I wouldn't have chosen the 34. I would have chosen the 55. If we have both this one and this one, the sum of these two is just the next one. So therefore, if you choose one of the Fibonacci numbers, the next one is surely not chosen. Or in other words, there are no adjacent ones as you have here. So here we have never adjacent ones, which means, in other words, that these representations are sparser. Because if you have a 1, there must be a 0 next to it. And so what is this good for? So it is good for, because here you have a comparison between the standard and the Fibonacci representation. The code word length, while I take a number m. So the code word m in the standard system is about log m. But in the Fibonacci statement, you can do the calculation exactly. It's about 44% longer. So you need more bits, which is a disadvantage. But the probability of the 1 bit, while for the standard it's just 1/2. If you take a random number and for every bit, so it's either a 0 or a 1, and all the zeros and all the numbers appear, the probability is 1. But in the Fibonacci, since the appearance of a 1 implies an appearance of 0 adjacent to it, so there are less ones, and you can calculate it. It's just 0.27. But if you take the average number of bits, so you have to multiply this, and here multiply by 44% more, but it's still, here you get 0.5 log m, here you get only 0.4 log m. So the number of the average number of 1 bits is less in Fibonacci than in the standard. And this can be exploited for plenty of applications which I want to show you. So here, take, for example, the standard numbers. So these are the standard numbers, 1, 2, 3, 4, until 14. And in Fibonacci, they would look like this. So you see they are getting longer and longer. And if we use these representations to represent numbers, we would have a problem. So what is the problem? Concatenation. Suppose that we have a list of numbers, 1, 11, 3, and 6. So here you have the representation in the standard way. That's 1, that's 11, that's 3, that's 6. If I transmit it, I would throw out the spaces between them. I would get this. This is exactly the same without the spaces. The problem is, how do I know how to interpret this? So I don't see the answer. This is the length here is 1 bit, 4 bits, 2 bits, 3 bits. How do I know? It's not obvious. So the usual way, what we do is to decide what is the longest or the largest number we need, and we pad all the numbers with zeros at its left end. So for example, here we have 11, that's 4 bits. I will represent all the numbers by 4 bits, which gives you 0, 0, 0, 1, and this one, and 0, 0, and so on. But this is a waste, because sometimes I have smaller numbers and sometimes I have bigger numbers. And then if I throw away the spaces, I can decode it because I know I have to read 4 bits, 4 bits, 4 bits. This is a waste. Look what we can do with the Fibonacci. Here we have the same numbers, 1, 11, 3, and 6. In Fibonacci representation, here you have the list. Here it is enough to add, for the padding, a single 1 bit. Why? Because all these numbers obviously start with a 1. They have a leading 1 bit. So if we get another 1, then we know that all the numbers start with 1, 1. But this serves, the 1, 1 serves as a delimiter, because I know that within a Fibonacci number, there are never adjacent ones. So I can just decode it, 1, 1, 1, 1. So now here's the next 1, 1, so it goes until here. Here's the next 1, 1, so it goes until here, and so on. And the numbers, of course, here it's almost the same, but for larger numbers, so I need only 1 additional bit per code word. Okay? So the 1 serves like a comma. But there's still a technical problem. The problem is that the code we get like this is UD, which means uniquely decipherable. We can decode it, but it's not instantaneous. Because instantaneous means that as soon as you get to the end of a code word, you know what code word it is. For example, look at this. What is the string? How do you decode it? So we can try to decode it like this. 1, 1, 0, 1, 1, 1, 1, 1, 1. Oops. 1, 0. 1, 0 doesn't, there's no such code word. So we did something wrong. What did we wrong? The first one, it wasn't 1, 1, 0. It should be 1, 1, 0, 1, and then 1, 1, 1, 1, 1, 1, 0. Fine. So in order to avoid this going back and so on, all we have to do is to reverse the code words. Because if we reverse the code words, and instead of putting the 1 bit at the beginning, we put it at the end. And then what we get is a prefix code. A prefix code is a code. I'm sorry that it's called a prefix code because it's exactly the opposite. A prefix code is a code where no code word is the prefix of another. So it should be called a non-prefix code or something like this. But that's the way you will find it in all the textbooks. So it's a prefix code. So all we have to do here, for example, these were the Fibonacci numbers. And what we have done here is just we take the number, reverse it, and put an 1 at the end. And then we have a prefix code. A prefix code you can just decode automatically. And this code is called the Fibonacci code. And I once drove and had a car in front of me. And when I saw its number, I had to stop and take a picture of the number. So they probably didn't know that they are driving on a Fibonacci car or something like that. And this is in our university. We also have so this number here is, you can see it here, it's the number 14. Yeah, it's the car number 14 apparently. So they didn't know that we have these little university cars with Fibonacci numbers. So about the usefulness, I won't have the time to go into many. Let me see how we going. Okay. The compression using the Fibonacci codes relative to other codes, we get better compression. We get, it is more robust than Huffman codes. You must have heard about Huffman codes. These are codes that compress. One of the problems, and do it optimally, you'll learn a theorem, a nice theorem, that this is a given distribution. Huffman solves this problem optimally. The problem with robustness is that what happens if there's an error? And whoever tries to transmit something over the internet knows that errors do occur. And sometimes you open up the radio and you're in the middle of a sentence. You don't understand. But very quickly, if you're listening, after a few moments, you synchronize with whatever is transmitted. And the same thing here. The first bits I get are perhaps not really meaningful, but then at some point it synchronizes. So in Huffman codes, since they're variable length, it can be that you have an error, and this error can propagate further and further and further, and it doesn't always happen. It can resynchronize, but this is this could be a danger, and Fibonacci codes are more robust than that. Then there is a way to do modular exponentiation, so even something that's used in cryptography, and finally on the rewriting on flash memory. So you see, there are applications in many different fields. I won't have the time to go through all of them. Let's see here. Okay, I'll skip through it. The better compression and dense codes. There is something called dense codes. I think I'll skip about that. Just giving you a final graph. This is one of the known compression methods. For zip is a distribution which is assumed to represent the distribution of different words in a natural language database. It's something from psychology, and so you know that it means more or less that the rank of a word times the probability gives you a constant. And this is an assumption. It's not exactly true, but there's a rule of thumb due to zip, which is pretty close to truth. So if you take an alphabet of size 100 or 10,000 or a million and so on, it's on a logarithmic scale here. The larger, you see how many bits would you use? About 10, about 14, about 18. You see it's more or less an exponential line. So it's a linear line on an exponential scale. You need more bits, of course, if the larger your alphabet is. But With Fibonacci codes, you need less. So this is Fibonacci 2 on the basis of 2, and only for very, very large alphabets you cross this line, and Fibonacci 3, you cross it. You also cross it at the end, but for alphabets that are so huge that you probably will never use them. So this is about the compression efficiency. And these are theoretical results. You can just measure them. About robustness, let me just speak about a few words. Suppose these are the different code words. You know the code words are of variable length, both in Huffman and in Fibonacci. Now, what errors can be bit flips? A 0 can turn into a 1, or a 1 into a 0, or the insertion. So suddenly some extraneous bit has been picked up, nobody knows where, or deletion, some bit being lost, and what happens there? Now, suppose this happens here, and so this bit is wrong. Yeah? So this long code word can perhaps be because of the wrong bit, be a shorter one, and then the next one will extend to here, and the next one will extend to here, and then sometimes it will resynchronize, and sometimes it will not. All these code words are wrong decodings. So what will happen? Here you have an example. This is the beginning of the Bible, King James Version. And we have encoded here with the Fibonacci code. Every word has a. Suppose there is a, and we have put an error. So what happens here, and you understand this because I can detect the end of a code word by the 2 ones at the end. So if there is an error in the middle, well, this code word will be wrong, but it will not propagate. If the error is in one of the 2 last bits, so if the 1 1 turns into 0 1 or 0 1 0, well, then 2 code words will be concatenated, so I'll lose 2. But it cannot propagate more than that in most cases. So in the beginning, God created the heaven and the, suddenly before, and the earth was without form and so on. So only one word. Huffman coding, so, and the father died off upon was without form. So you see that here it resynchronized, but only after a few words. In SCDC, this is another form. So you created the sin and of the Jacob again called, so completely lost. So there are. This is not robust at all. So there are encoding functions, compression methods that are very sensitive to errors. You have an error, it can be wrong for almost everything. So this is one of the advantages here. So, okay, modular exponentiation. Okay, that's more mathematic. Let me skip about this. The idea is to to represent the modulos. Yeah, we want to calculate a to the power m modulo n. This is something which is done in cryptography very often with very large numbers. So you can't really do a times a times a m times, because m can be 2 to the power of 400. And you cannot do 2 to the power of 400. Oops, I did myself. Okay, so what you do it exponentially. So you prepare log m basis elements, and then you square them repeatedly. It doesn't matter. What you can do instead of using, like we did before, instead of using the binary powers, you can just use the Fibonacci numbers and then have almost the same, but then instead of squaring, you just take the 2 previous ones. And so why does it, how does it connect to the Fibonacci code? Here you need log m squarings. Here you need log to the phi m squaring, which is 44% more. This is the same 44% we had before. But the number of multiplications is like the number of 1 bits. So here it is 0.5 log m. Here it is 0.4 log m. So doing it with the Fibonacci code saves you about 20% of the work, which is good. Here you have another rewriting on write once memory. What is a write once memory? These are old ones. Perhaps Professor Gallo remembers still. They punched paper tapes in order to encode some instructions externally to the computer. Or there were punched cards. We spent a lot of hours to punching these cards. There were machines did a lot of noise to write on punched cards. Today they're gone. But even the USB stick are write once memory. Yes.
Because the card from IBM,
yes, yeah. They were standard cards. They had all this corner missing in order to know how to put them, and they were standard size, standard color, standard everything all over the world, and the standard absolute standard. Now, what is the constraint for all of these? You can change from 0 to 1 very easily. It's like adding a hole here in, or adding a hole. If there is a hole, you can add a new one. That's no problem. The problem was to go from 1 to 0. It means once you have a hole, you cannot really erase it. So there is a way here to erase it, but only in blocks, and it takes a lot of time. And therefore, there was an entire study of how to devise a rewriting code. What is a rewriting code? For example, Rivest and Shamir have an algorithm to use 3 bits to encode 4 values. 4 values, you usually use only 2 bits. But in 3 bits, I use 2 values, but I can use them twice, which is very nice. So you have, in the first round, you write something, and then whatever is written there, in the second round, if you write something else, you only add once. So the 0 can turn to a 1, not the 1 into a 0. And that means that the ratio, you have 3 bits, encode 4 values. 4 values is, in fact, 2 bits, but twice. So you write 4 bits of information within 3 bits, which gives you a ratio of 1.33. These are called rewriting codes. This is very nice. How is it connected to Fibonacci? Here, take the idea of using a Fibonacci in the first round. So I'll give you, because we are using the fact that there are no adjacent ones, here's the idea. Every 1 is followed by a 0. So use these 0 bits, and you know where they are because there are 1 bits just in front of them, in order to encode the second round. So how can we do this? Here's the algorithm. First of all, consider a block as a binary number. So I have 50 bits. I consider it as a 50-bit number. It's a pretty large number. 0, that was 0. 1, recode the block in Fibonacci representation. So the number is 700 million. Write this number in Fibonacci, which means that there are no adjacent ones anymore, but you used more bits. 3, add ones without violating the constraint. So there are many zeros there, but add the ones, because after you've encoded the first round, you don't need the information anymore. And then use the bit following the ones in the second rewriting round. So here's an example. We want to encode the number 5 million something, whatever this is. This is 3 bytes, so 24 bits. And then the number 777, which is here written in binary. That's 14 bits. So how do we do it? This is the number 5 million, and you have here 33 bits or something like that. No, this is already, excuse me, this is 1. So this is already the number recoded in Fibonacci. So the 24 bits, this is 24 bits. recoded in Fibonacci, it's 33 bits. Yeah, and you see here there are no adjacent ones. Then we add the ones, because here you see, here you have 3 zeros. The 3 zeros, you can just change this into a 1, and there are still no adjacent ones. And here you can even add 2 ones. And sometimes here you can't add anything, because there are 2 zeros, but, there's no 1 can be added. So these are the additional ones. And then now look at the numbers, at the zeros after these ones, the yellow ones. Not this one, not this one. But the yellow ones, these are places where I know that there is a 0 bit. So I can reuse them. These are 14. So I can just plug in these 14 bits here. So how much have I used? The data was 24 bits for this and 14 bits for this. This is 38 bits. But the ratio, I have used only 33 bits. So the ratio is more than 1.15. So it's not as good as what we saw before, but still it's another idea. You know? So decoding is very easy. This is an automaton, and you can just decode it without any problem. Here's my conclusion in order to stick to the 35 minutes. This is a citation I found in a book in 1985. It says the following: the Fibonacci number system, so-called backnotes, is another remarkable and remarkably useless number system. That's a quote from, of course, Professor Geller knows me that this is exactly the quote you need in order to immediately send you home and try to prove that this guy is wrong. This led to the codes and to all these numbers. So the references, so these are some of the references of the papers I've shown you here. And if we really want to finish that, this was the first slide. You remember I called it the usefulness of the Fibonacci system. So perhaps we should recall the talk, the usefulness of a useless numeration system, and that's the way. So here we are.
Questions? We do have one more person in the audience who remembers punch cards. Yeah, any questions? Any questions? So,
yes.
Are there a few applications where Fibonacci codes are being used?
Well, these were just 3 of them. The main, there are a few. I'm not really aware of people who do modular exponentiation with Fibonacci numbers, even though it's proven that it's better. But for Fibonacci codes give you less compression than, say, Huffman coding. So if it's very important for you to have very good compression, you wouldn't use the Huffman, because Huffman code is custom tailored to the distribution, and Fibonacci codes are constant. So they cannot be optimal for everything, obviously. But very often you don't care so much if you have 22% or 27%. It's not really, but you care for other properties like robustness. If sometimes, if you're afraid of having errors, I know that in your storage, the computer doesn't introduce so many errors, but for data transmission, you know very well how error-prone they are. So you don't want to lose all your data. Then you say, I'll prefer not to compress so well and to have it more robust. And then Fibonacci numbers are very good. Then there are obviously others, but yeah, they are used. Yes.
Um, Thank you. Let me echo that questions about the robustness of data transmissions, right? Is there any alternative solution they use for internet these days to?
What they use first of all, what they do, in order to reduce the damage, they transmit the data in packets. So you don't really transmit gigabyte of data without you put it into blocks. But it's a matter of trade-off. The larger the block, the smaller the block, the more you lose on padding it and so on. But you reduce the effect. So if you do it anyway and with small blocks and with a lot of padding, then you might as well do it with Fibonacci codes where you don't need that, and it can be more effective. So people do this.
Thank you.
You're welcome.
There is a question on Zoom.
Oh, sure.
Yeah. So the question is, can I become a data analytics, then progress into a data scientist?
It's not really a specific question for
Okay.
Professor Klein.
Yeah,
Start by chat and
Yeah, I
ask
guess
your questions.
Yes.
Okay.
Okay, so we have to buy one of those fake fires. Oh, and just
but by a true one. It's,
really, I want to go into two directions. One of them is, so you've had an illustrious career and you decided to retire very recently, or maybe you were forced to retire. So we have some junior faculty sitting here, and what would you advise them how to be successful in this field from your long experience?
okay. You want the true answer or the okay? Well, one of the advices I can give is to plan ahead. Perhaps something which we didn't really do. So the listener and ask your advisor or your. Is there a mentoring? We have it at our university. New faculty are, once they are accepted, every new faculty member gets a mentor, which is one of the more senior faculty members that helps him in his first steps, and perhaps even more than for the first steps for a few years, to tell the new faculty member, for example, that it's very important to go and to submit proposals for getting grants, and to send papers to the good conferences, and not to be not to try to have as many papers as possible by sending to there are predatory journals and predatory conferences that are not worth. And if you see a conference that accepts almost everything, then be aware of it. And try not to send them, even though you're tempted to get your paper. You had this publish or perish paradigm. I don't know if it's still available.
Yes.
So you should, when you have a good paper, you've written a good paper, get advice from senior faculty where to send it to. usually they will be able to tell you, well, this is not really a result that you'll get accepted at the best conferences, so try this one. Or they will tell you, well, I got such a nice paper. All of you probably will get letters, as we often do. I saw your paper about this and that, and was very impressed about it. And you clearly see that the guy who wrote you has not a clue what the paper was about and has not even looked at it. And why don't you want to republish it with us? And so on. So be aware of these things, and have to work hard.
Okay. If any one of you wants to follow up, you can certainly do that, but maybe a little later, because there is a second direction where I want to take this, which is we are going through the biggest upheaval in computing thanks to AI breakthroughs that I've seen in my whole career. And it makes me feel a little bit, when I was an undergraduate student, I still had to take a course in assembly language programming. Well, a few years later, we didn't have to take, or the next generation of students didn't have to take a course in assembly language programming because you had good higher level languages. It started with Pascal. In a way, very few people really learned assembly language programming from that stage. And now I'm a little bit afraid that we're in a stage where students will say, well, we have LLMs, we have LLMs that write very good programs, and why do we need to learn programming anymore? And when this whole LLM thing broke, I was thinking, oh, I'm teaching PLSQL. Nobody knows that language. LLMs don't know that language. So I took my first homeworks from the class and I put them into ChatGPT version 2.0, I think it was, and it spit out a perfect solution the second time. The first time it had one variable wrong. The second time it had a perfect solution. And I just gave the most complicated midterm exam that I have given in my whole career, because I had to design it in a way that even if students use ChatGPT, nevertheless, if they don't know anything, then they're going to fail it. So it was really very challenging for me. So where are we going with all this as a long-time educator? Where do you think we're going with all this?
Well, it's a very, very tough question, and I know that not only us, but we had many discussions at our university, especially for how do we check homeworks now? Because and in programming, that's one thing, but imagine in the social sciences and in where they have to write works about whatever topic, and today you go so. Even years before, the people just went on the internet and gave us a work that was written in some university at the end of the world that nobody knew about it. But we learned very quickly to see that if the work seems to be on a too high a level, or the English is too good to be true, then we just checked a few words and then we found exactly the same. Whatever the student found, we found it too. And so our committee for our disciplinary, they had a lot of work to do. But today you can go and ask ChatGPT, just rephrase this and that, and then it's very hard to find. So they decided, first of all, not to prohibit the use of ChatGPT, because if you can't fight them, then join them. So students have the right to use ChatGPT or whatever they want, Perplexity, or there are even better ones and everything. But they have to declare it. So after I've used ChatGPT to this and that, and our job is now to evaluate the work, not so much as how much work did the student do to find all this information, what did it do with the information, and how did it present it, and so on. I think it's not so much different about writing books. You can ask today ChatGPT, you have an idea of some plot, give it to ChatGPT, it will write you some Harry Potter 9 or whatever. This will be, but still you need I think the ingenuity of the people will only go increasing, and therefore I'm not so much afraid about programming languages. You know, if you the assembly language, by the way, is still used until this very day, because there are, if you try to write something in Python or even in C++, it will take an awful lot of time. And once you start working in some real company that needs to produce something, your boss will tell you, well, that's perhaps correct, but we need it twice as fast. And well, you have to understand what you did in order to correct it. And it will go more to to devise better algorithms and so on. But if you don't know how to write in assembly language, or say in Pascal or whatever language, even in Python, but in C++, then you will not know how to improve the things. So I'm confident that whatever you learn, even if it is very basic one, perhaps you won't use it as much, and perhaps you will waste less time on sitting and thinking, how exactly do I do input-output in C++ with all the things, and waste tons of hours when you can in a second get it. But I don't see yet the ChatGPT giving you the better algorithm, and you know that algorithms are improved all the time, and the better data structures. So what you learn in very basic stuff, you can say the same thing about math. You know, the first year of calculus or of algebra, why should you bother how to see how to prove all the theorems? You will never prove them again in your life. But if you didn't see the very basic proofs, you won't be able to do the more complicated ones you need today. And therefore, I think we'll not retire yet at the age of 30, because ChatGPT will take over all our jobs. So don't be afraid.
Okay. Well, some of the students in the audience are worried. Will they have jobs when they graduate? Or will it not be necessary to teach anymore, I guess?
I think probably most of you will work in works that do not exist now. Because if we think in the early years when we studied, did we know exactly what we are going to do? Unless you're a physician or a lawyer, or even the lawyers have to know today much of the things that they didn't dream about when they started their studies. So it's very possible that whatever I found out that most of the things I learned in my undergraduate students, even many of them I used many years later. But I used them. Of course, I learned many things also which I never have used. But I think you also learned Latin in school, did you?
4 years.
We had many years of Latin, and you tell yourself, why do you need Latin? Nobody really speaks Latin, unless in the Vatican. But they don't really use Latin as a living language. But what we learned in Latin is to use grammar. And once you have the Latin grammar and so on, then learning something new was so much easier for us. And so it was absolutely not a waste of time. What we learned in high school. And I think the same is true today. You can't learn mathematics without having a basic course in algebra and calculus, and you learn there are many things which you need only at that moment, but it is a basis of what you're going to learn later, and it will help you understand and have insights much later. So don't you can trust your professors, and I don't know. I think it's the same here as in all the universities of the world. We are not teaching a course just because it's there already for 20 years, so it has to continue on. I'm not talking about the basic things, but yeah, so it took also years in our university to get rid of the assembly language course, and there are all the time new courses getting up, and we changed the curriculum, and we changed the basic programming languages. But it's good to learn a programming language. It doesn't really matter which one you learn. You learned Pascal?
Yes.
Pascal was my first and Fortran. 77. And nobody uses that, but well, it took me 2 weeks to learn C after we know all the others, and this is the same for you. Once you know C and the Java and so on, it doesn't really matter which one. Once you've grasped the idea of programming, translating it into whatever programming language is a technical matter, which every student should be able to do without any problem. Yes.
Thank for your answer. I plays a devil advocate here. For example, like you're saying that, okay, so coding, right? You have some basic knowledge or understanding, and then like it's fine to use the tool to generate some code and use it faster and so on. In school, it's okay, because in industry environments, that is the black hole right there. Because if we don't have a deep knowledge about what is the code doing about, in the detail, right? So there's a lot of black hole, like crashes along the way. That like if the software engineer is not trained well, then how can they use the tool in a reliable way? How can we? Right, that is one thing. I would like to get your comments on that. The second thing is that you're saying, okay, so trust your professor. I'm a professor too, but to be honest with you, right now, the trust is less already. Lose the problem. I just discovered, like a couple of days ago, there's another professor told me, hey, what are you ChatGPT to grade the student? Okay, what the heck is going on? Because like it's not okay. He doesn't have understanding of what the student is doing.
Yeah.
Get the grade out and get his job done, and nobody know.
Yeah.
So the grade is there, and but this is happening at a larger scale. We mean like scale to hundreds students, classes, and so on. It's not just in NJIT, but it's across the campus and so on. That is not a problem. So it's come to paper review. So I heard it's very typical that students using ChatGPT to review paper and submit a review to conferences. So this is shocking to me too. Mm-hmm. So what are your comments on that?
Yeah, when I said trust your professor, I didn't mean one. I meant, you're of course right that you have many professors and get your opinions about from several ones. You have of course to know what to do. About your first question, in industry it's a little bit different. But what I wanted to say is sometimes in industry the way of programming is quite different of what you learned. And I think the rule of the university and is not so much to teach you technically the programming itself, but it's more to teach you to think. And if they succeed in that, that's already very good. I know that in Israel, when our students go and go out to get a job, they are interviewed, but they prefer a university graduate without experience to a non-graduate or somebody with less teaching, or you can learn programming you don't need a university to learn programming. There are courses, I'm sure that here you can learn within 3 months, 6 months, and so on, and you get immediately a job, but you will not advance on your job because you're kind of a low level. You don't have the background you get in the university, and this is a big difference. So whatever you need in industry, you learn then in industry. So you have something very specific and perhaps a new language or something. You will learn that. That's not, once you know how to learn, how to teach yourself and to open a user's guide and so on, you'll find it on your own. This is what you should learn. It's not the specific manner. We have to grade the students, so we have to give them exercises and we have to give them exams, and but this is not the main point. And so also for teaching in large classes, it's I think the side effect you get is much more important than the specific points, and I hope that will help you ultimately.
Okay, thank you.
Yes.
So follow up with your questions. So from my perspective, industry right now, they do require students to have a set of skills, like how to speed up the process and everything. So there is 2 things that an undergraduate like me have to master in order to find a job in the industry. We have to be at the same time learning, understanding the convention of knowledge, how to build a low level to level up to the high level one, and at the same time learn to use the technology, use ChatGPT to boost up our work. And you see here there is the trade-off between the conventional and boost up the speed, because if I focus more on the conventions, it is less likely I'm not going to ask ChatGPT how to do my work. So from that, it is hard for me to learn to use the language, how to prompt engineer when I be in the industry. So what is the break point between 2 of these skill sets that I can learn in the university years, so that I can leverage my skills to be in industry? Or
my advice would be, since you don't really know today what interviews you're going to do in 5 years or in 3 years, and you don't know what the company you would like to work there will concentrate. So sometimes I see we need people who are experts in natural language processing. So natural language processing would be very good if you know another language, Spanish or whatever. But I wouldn't tell you now go and learn Spanish if you don't know it yet, because you don't know. Perhaps it's a waste of time. So the only advice I can give you, take the whatever you know, whatever the university gives you now as a curriculum. They tell you you have to learn this course and this course and the 2 of these courses and then 5 of the other ones, and there are quite intelligent people who build up the curriculum and give you the best chances. Now, if it will be custom tailored to your specific needs, this is a chance. You know, you could just as much ask me what to invest into, which stock exchange. I don't know which one will go up. But one thing I know, whatever you invest to now, it's not a waste, because even if you, I took a course in, so I mentioned natural language processing, or in artificial intelligence, or in complexity of algorithms. You took a course, okay, the company will see, well, we don't need it, but if this guy got a good grade there, apparently he's an intelligent guy. If he learned that, and that seems complicated, he's probably able to learn also something different. And they will accept you for the very fact that you studied it, and not for the content of what you studied. So this is the best you can do. If you get excellent grades on whatever you did, I think many companies will appreciate it and don't ask what exactly was it. But they see a guy who got very good grades on a variety of different things. He has good skills. This one, I want, if he learned that, he will learn whatever will teach him.
Okay, we're at an hour, and I promised when we started the speaker series that we'll keep things to an hour. So thank you very much again.
You're welcome.
And you can make your email address. If you have more questions, I can share the email address.
Yeah, sure.
And again, thank you for coming today.
You're welcome. Oh, okay. No, it's not my laptop. I
Right.
almost
It's also
took
not also not your microphone.
Yeah.